We should start this morning our lecture, and the first thing that I would like to do is to remind you that I sent yesterday an email um, where I indicated that uh, we are going every Wednesday instead of just having 2 hours there for office hours. We are going to use these 2 hours for me to solve problems every Wednesday from 4:30 to 6:30. We are going to solve problems which I think will help you with some of the fundamentals that are important both for homework and for the class. And then I'm not going to solve the homework, obviously, but I will try to solve problems that help you with the fundamentals. So that's what I wanted to do. And the other thing that I wanted to also mention is that I have that make sure one thing that there is before I leave that topic, that the Zoom link for this session is not as part of your Zoom in the for your class. Yes, it is, but at the same time you will find it as part of your Zoom, not as the traditional link that shows the class, but it's going to say problem solving session. And I don't know whether I sent you an email with a link again, but I don't think you need that because it is under your Zoom. I have sent the other section the link. Since you have it available, it's going to be easy for you just to get on Zoom. Unless you tell me that it's going to also be convenient to email you the link. So you don't have to get on Howdy to connect. Do you want me to email you the link? Is that convenient or not? Okay, I will email you the link because I understand, otherwise you will have to, I don't want to crowd your email box with emails, but since it's convenient, I will do that. At least it's convenient for me because I don't have, if I want to get on a Zoom, I don't have to go on Howdy and then from there find it. That's pretty good.
Professor?
Yes.
If we wanted to during these problem-solving sessions, if we had questions about the homework, could we ask them, or is that just strictly?
This is, if it is, you will see I'm going to solve problems that are connected. Yes, at the end of the session, you could, not while I'm solving the problem. Then we will do it at the end. I will start solving. Maybe I will have an hour or an hour and a half, and then I will leave some time. I think an hour is plenty for solving problems. It might take me a little longer depending on the problem, but after that, yes, you can ask me.
Okay, thank you.
You're welcome. The reason I'm doing that is because I have to tell you, I received, and these are very valid questions. I received questions via email, but a lot of times the answer is not easy to put it in an email. So, yes, I also want to say one thing. I saw a note about recording the session. There is a reason I don't want to record the session. Because if I record the session, not too many people will come. And then they will have exactly the same questions as before about the homework. So I want people to make it as much as you can. I know that it is convenient, and I understand for those who have some serious conflicts at that time. But at the same time, if I do it formally, half of the students will not show because I know your calendars are really crowded. But it's not helping you go over one more video. It's gonna keep, if you're not there in person, to even ask me a question in real time, it's not gonna solve your fundamental questions. You will still have questions about some fundamental things, And as I said, what I found it difficult is a lot of times you send me a question that cannot be answered via an email. At least it's going to be difficult unless I use one page and I solve examples, which I cannot do because I receive a lot of questions from different students. So sometimes when I say, please come to office hours, it's not because I don't want to respond to you, it's because my response will be long and it may not necessarily help you. Email is not the best way to communicate a question or try to do some understanding. That's why I insist on office hours or during the class or right at the end of the class. It's better to ask me a question and I have the opportunity to explain in real time. Okay, that's why I'm doing that. So there was a reason for not recording it. Now, if you have a serious conflict, then what I can do probably, because I can record all sessions, I will record it, but I'm not going to post it unless you tell me, and I will give you access to the video if you have another conflict with another class. How about that? So I would like to encourage as many people to come and ask questions, not just go to a different video, you know. I don't know. I mean, I'm just trying to get people to get involved and ask in real time. There is so much you can gain out of it. Any other questions?
Professor,
Yes.
what time would this meeting be?
4:30, the same times I like office hours.
Oh, okay.
4:30 to 6:30. Do you have a standing conflict?
I have a class at 5:35, and I think there are other students that do too. I think computer architecture 350.
Okay, is it 5:35?
Yeah.
Well, I can from 4:30 to 5:30. I will solve the problems.
Okay.
All right, and then it's better if you have a question to get on Zoom with you. If it's just unless it's just a simple, what was that? Was that coefficient X, Y, and Z? But if it is like, I don't understand how to do that, it's better if I have a Zoom meeting with you individually, all right? So I will tell that, of course, I will not be able to do it with 60 students individually, but for situations like that, I think if you try, I cannot do it before 4:30 because I have the other section that goes up to 4. It goes up to 4. Yeah, almost up to 4. So by the time I get out of that classroom, because it's face to face, and I find another place I get to another place, I can sit and connect. It takes a good 15 minutes. That's why it is. I give myself some time to do that, like half an hour. Okay, that I try to explain. The but the first 1 hour, if you make it, it's going to be good enough. The other thing that you have not done so far, and we are going to start this week, I'm going to give the first homework to the teams. Get to meet the other members online. I meet the other members of your team. And then please feel free to discuss with the other members of your team different problems, even the homework. I don't care, as long as, of course, in the individual case, you submit it individually. You write the solution yourself. I don't want you to copy. I want you to discuss concepts and then learn from each other. That's perfectly all right. So if you reach out, and I will also, I mean, this is giving me a good opportunity to make that comment, meet the other members of your team. Yes, you will do the, so here is the difference between individual homework and team homework. You can solve all of the team homework as a team. And then I said, I want only one PDF from the whole team, one submission. Individually, of course, you're not going to solve it as a team, but you are free to discuss it. All right. I mean, you're not gonna have somebody else solve it for you, but ask for help. It's okay. But you will have to sit down and write the solution. Okay? That's the difference. So it's okay to discuss and say, by the way, how do you do X, Y, and Z? But don't say, how do you solve this problem? All right, that's different. But how do you do X, Y, and Z? I want you to identify what you need to know to solve the problem and ask the question about the things that you need to know. Find the information to that and then solve the problem. All right, there is a difference between finding the solution ready or asking about the things you need to know to get to the solution. They're two different things. Is that clear? I'm sorry if it sounds kind of confusing, but as you practice it, you will understand what I'm saying. Any other questions? So I will record it, but you need to, I will give it to those who have a conflict with a class or a senior project capstone. Okay? All right, so what I would like to do next is to, we are going to solve some problems. We are going to practice with some examples. We are not going to yet introduce new topics. We are going to stay with the divergence, but from divergence, slowly, we are going to move to the electrostatic fields. And I wanted to say one thing as I will start here and I get to the, so you will see something that I have already uploaded. I will share my screen. So you should see something that I have already incorporated in on the main page. And I have also included the lecture recording. So this is what you have already seen. Now I will do one thing so you don't hear that small echo. For a moment, I will turn this off. Can you now hear me?
Yes.
Okay, perfect. So we're gonna, so that sounds clean. Okay, so we'll start with that. You remember what we said. This is the divergence theorem. It's extremely important, all right? That what does the divergence theorem say again? That if you have a vector, and the vector is here, and this is a vector field, for example, all right? But it's a vector. It applies to all vectors, rather. And then the divergence of this vector, if you take it, and then you integrate this over a volume that incorporates an observation point, P, all right? Let's assume that this is a point in space. We have set it there. For a moment, there is nothing. We don't know what it is in this point, all right? This is just the divergence theorem. We have a point P, and we encapsulate it inside the volume V, and this volume is surrounded by a closed surface S. We said that the volume is a scalar, but the surface is a vector. And we also mentioned that the direction of the surface is characterized at every point, can be different, and at a given point is the vector normal to the surface at that point. That's the direction of the surface. Okay. Now it's the outward in this particular case. direction of the normal vector. All right, so the volume is enclosed by a closed surface. It does not have openings. The surface is totally closed and encloses fully the volume. And the vector, the direction of the surface, is the outward direction of the normal vector at every point of on the surface. Okay, these are the definitions of the various entities. So here, if we take the divergence of a vector and we integrate it over this volume V, divergence theorem says that this is equal to the closed integral, the round thing, so it's closed integral of this vector on the surface that surrounds the volume. And you see that there is a dot point here. There is a dot. This is inner product, as you can see, this dot. And probably I can make it a little stronger to show. This is a dot product between vector A and the vector ds. Okay, now we take this to electrostatics. All right, so we give some physical meaning to the vector rather. But to get there, we apply it on the quantities in electrostatics that we have already seen. And we define these quantities here again. So Q is the charge in coulombs, is a total charge in this particular case. F is the electrostatic force in newtons. And I gave you the Newton here. Here there is one thing that I wanted to, which I have corrected. As we will see later, when we have a three-dimensional problem, Coulomb's law has a 4. In a three-dimensional problem where you have a point charge, Coulomb's law has a 4 at the denominator. And in two-dimensional problems, it has a 2. Accidentally, last time when I made the lecture, I had the 2 there left over from a problem that I had solved in the past, which was two-dimensional, in 2 dimensions, but I have already corrected it. So this is the correct formula, all right, in 3D, and I will write it here, 3D, the force that is exerted by a charge Q located at one point. So a charge located at one point is called a point charge, is given by this formula. That is Coulomb's law. And then here I give you epsilon naught in numbers and units. And we said that epsilon naught, it's interesting, it has units of capacitance per unit length. So keep that in mind. It's interesting because practically it shows the capacity of a medium to store charges. That's how we define it, but we call it the dielectric permittivity. It's dielectric permittivity, or we call it the dielectric constant. And A sub r, alpha sub r, as your colleague is asking, is the unit vector. We said that every time you see a hat, you see this hat here. Every time you see this hat here, that means unit vector, and is unit vector along the direction, which is here, along the direction of the line that connects your source, which is your point charge, with the observation point, or with your the person who is observing, all right, or the place where you observe from, or the place of another charge, all right? But this is, in this case, if your source is the Q, capital Q charge, another charge placed in the space near the capital Q, a small q, which is an observer, or another charge, you can call it an observer practically, then this charge feels a force F. That's Coulomb's law. And this force F is given by this formula here. Then what we do is we define the electrostatic field. All right, we call it electrostatic because Q, the source, is a static source. It does not change with time. The field, then, we define a new entity, which is called the electric field, E. And you remember, the force is what is real. The field is a mathematical entity. We introduce it. Why? Because when we have the field like that, we have eliminated the impact of the observer, where the impact of the observer is this Q. All right, in here, to find the force, you need to know, you have information about the observer. But to find the field, you don't need information about what is happening at the observation point. You only need information about your source. That's why we introduce it. So here, this is given by Q. All right, now, as we said last time, we define the electric flux density. It's a definition. It's a new vector, which we call D, which is, it's analogous to E. And practically, the only difference is that we multiply the electrostatic field by this constant epsilon naught, and that gives us D. All right, this is the electric flux density. And why we called it flux? Because it reminds us of the flow. So when you have a source, and then you have the electric field, that starts, is created by the source as a vector. The way the electric field spreads out, all right, it defines us of the flow of water, for example, of the fluids. It defines us of things that we have observed in our real life. Even if we cannot see the electric field, but we have seen how fluids, how the water is distributed when you have a spring, a source, where the water comes out, we have seen how it is spreads out and so forth, and how it flows. So we don't talk about flow of an electric field, we'll talk about the flux, but in reality, the flux shows how the field distributes around the source, from the source out. Or if you have a sink, that it absorbs it inwards towards the sink, all right? So it shows how it all goes into the sink. That is called the flux, and it's D. And it has exactly the same direction with E, and it just it has a scalar multiplier. That's all. Now, what is extremely important here is this one, because this is going to give us a very important relationship that we will see later. This tells us here that if we integrate the divergence of D on a volume that surrounds that point where the D is you remember the divergence of D, this is a differential, the del is a differential operator. The divergence of D is a function that applies at each point, all right? So when I calculate the divergence of D, I calculate it at a point. So if I take then this divergence of D and I integrate it over the volume V, then that, of course, according to divergence theorem, becomes a surface integral on a closed surface. And then that is equal to the charge that has generated that field, or is equal to the charge that is in enclosed by this surface, to be more accurate. Okay, that is extremely important. Why is that? Because we can use this here to find the expression of the electric field without even knowing Coulomb's law. Is that not crazy? Is it like very interesting? And that's what I wanted you to do here. And then we'll go to calculate then the field and the electric flux density vector just by using the diversity, the divergence theorem. I always keep saying diversity. So at this point, I will add a page. Okay, and then so we can do the calculations. Let me prove to you that just from here, I can develop the formula that I got for the electric field using Coulomb's law. All right, you remember what is the formula I got? This one. I will get this formula independently of Coulomb's law. All right, so how am I going to do that? So I will say here to be an example. So example. So calculate the electric field that is due to a point charge Q, as shown below. As shown below. Okay, so here I have a point charge Q. Since it's a point charge, I'm going to consider the cylindrical coordinate system. All right, so I will place here, of course, the Cartesian, because we always define the cylindrical on the basis of the Cartesian system. All right, so this is X, Y, and Z, but we are going to be, since the point charge has spherical symmetry, you know, it is at the center of the coordinate system, then I will consider a volume which is like a sphere. All right, this is really very, all the time, you go for the simplest thing. The simplest thing for me here, since this is to use the symmetry of the source. And the source it's a point, so it has spherical symmetry. So I'm going to describe in green this sphere. Okay, it's not perfect. Anyway, this is the sphere which I will consider as my volume. So here, this is the volume that I'm going to use. I will do it like that. I will do a better later. Okay, this is the volume, and this volume is V. And the surface of this volume is here. That's surface S. And what did we say? That the direction of the surface changes at every point of the surface. Since this is a sphere, can you tell me from what you know from a spherical coordinate system, exactly what is this N? Could you identify the N, since this is spherical surface? What is the N? from what you know about a sphere in the spherical coordinate system, where n equals what unit vector? Do you agree? Yes? If yes, why? If not, why? Do you agree that in a spherical coordinate system, if I write here a line, let me see. If I write this line here, okay, this is the radius, all right? The radius has a direction. What is the direction of the radius? Is this one. Do you agree with that? Is that not the unit vector along the radius of the sphere?
Would it be like that because it would be perpendicular to the tangent of this point?
Yes. Yes. And A sub r is perpendicular to the surface at that point, and N is perpendicular to the surface at every point of the surface. So N is that. So that is the first thing that you identify. And then what is the next one? Now we apply the divergence theorem, and on this volume V that says the divergence of this of D for the field that is created here, we have a D, and D is equal, if we are in free space, epsilon naught E from definition. Now, according to divergence theorem, this is equal on the surface S, which is here, of D, excuse me, D dot ds. Good, so ds is what? Ds is a vector, and therefore is n ds, okay? And n is a sub r ds. All right. Now then, what do we have? That this one becomes from 1 divergence dot n ds, or equal to divergence dot r a sub r ds. Okay, so practically, let me add one more page. So practically, what we have here is the product of D dot A sub r is what? What is the inner product of a vector with a unit vector? Is
Scalar.
this one, is the component of D along that unit vector. In the spherical system, how many components can a vector have? So in the spherical system, generally, D would be dr a sub r plus d phi a sub phi plus d theta a sub theta. Do you agree? Yes. And if I take the D inner product A sub R, what is it going to give me? dr. Do you agree? Okay. So now what I have is that the closed surface integral of dr on this surface ds equals, according to the divergence theorem, equals Q. All right, and you remember the divergence theorem is from here, up here. That's what I apply. So now the whole thing here got me down to this expression. All right, but let me write it here for you to see it. All right. Now, if I have spherical symmetry in my source that excites a field, what do you expect the resulting field to be? Is it not going to also be spherically symmetric? Do you agree that with this argument? In a free space, in an infinite medium, if you have a source that has spherical symmetry, the field that results from this source have the same symmetries. Would you agree with that? Yeah, I mean, it makes sense, all right? Why would it not have the same symmetries of the source if the medium is all open and it does not have any things in there? And the space is uninterrupted with anything, by anything. Okay, so therefore D is spherically symmetric. So let me write here the observation D. So in fact, to be more accurate, we'll say Q is spherically symmetric. Therefore, as a result, D is spherically symmetric. And as a result, E is the same. Okay, this is also an assumption. All of these are important assumptions. These not assumptions, are important observations, I should say. We assume that the source is spherically symmetric. The rest is an important observation. Okay, why is that an important observation? Because then it tells me if D is spherically symmetric, then the value of D on the surface S is always the same. Do you agree? What does spherical symmetry mean? Spherical symmetry means that for a given R, so spherical symmetry is for a given R, then the value of D at R is independent of what? Of phi and theta. Do you agree? Do you remember the definition of spherical symmetry? Now, this is, yes, question.
I was gonna say, yeah, that makes sense. I didn't previously know that, but
Okay, yes. You know, we have seen it. I have to tell you, probably you knew it, but not articulated like this.
Yeah.
Because, yes, we have seen, but this is the first time we articulate it like that. I agree. And that's why we do that here.
Okay.
Okay.
I
Now,
have a question with,
yes, go ahead. Question.
so uh how come like when you decide when you like designate like that normal vector like
Can you speak a little louder so I can hear you, at least from me? I cannot hear you very well.
okay
Yeah, perfect.
how come when you designate like that normal vector um in with the head on is equal to like a sub r, um how do we know that it was going to be in like that r direction? Is that just due to the fact that like obviously since it's like
Sorry.
in of the sphere that like it has to be in that r direction like
Yes. It's from the definition of the sphere and of the spherical system. All right. By definition, in a spherical system, the direction of a sub r is always outwards. The direction of this is always outwards. And by definition, on the surface of this surface that is enclosing a volume, it has a direction always pointing outwards.
okay. And then when you were even like some of the previous ones you were saying like what r is, sometimes we use capital R. Is that,
Yes.
did r represent the radius of the sphere or is it some other distance?
No. R or capital R, sometimes they are the same. All right. We use them depending. You will see them also be used interchangeably. They are the same thing, and they show the radius of the sphere, of any sphere, with the center of that coordinate system.
Okay.
Sometimes also, so when we are here, all right, with this, a lot of times, so always this little r, and many times the capital R, when you have a, always, let me just be clear, in a spherical coordinate system, always the lowercase r indicates the radius, always. Now, in cases where we have a charge at the center of the spherical coordinate system, then also that radius can be indicated with capital R. When we have two charges, and independently of a coordinate system, the distance is always indicated by R. All right?
Okay. So
Yeah.
when it's one, it's the radius. When it's two, it's the distance between the charges. Gotcha.
Yes, exactly.
Thank you.
Thank
I was just confused.
You're welcome. Sometimes also you will see if your charge is at the center of the spherical system, sometimes, either in my notes or in multiple books, you will see capital R used also as the radius because they happen to overlap. See? Because if your source is at the center and I have another charge here, not only this is a distance R, it happens to be also the radius of this surface that goes through the other charge. Okay? And that's why you see it used interchangeably when you have a charge at the center of a spherical coordinate system. But in reality, the basic definition for R is as the distance between two charges, or between the source and the observation point. All right?
All right. Thank you.
You're welcome. Okay. I will leave this other here and erase this part here. I think that is clear if I do this like that. Then it's going to show what R is here. Okay. Now, let me continue. Therefore, if D sub R is the same with a spherical symmetry, D sub R, or first of all, any vector which is spherically symmetric is independent of phi and theta. And therefore, on a given surface, this bar is on a given spherical surface, this bar is constant. Do you agree that? Because it's going to only depend on the radius. All right. You see this one here? It's going to only depend on the radius. So what happens is that this bar is constant. So then I will say here, conclude, therefore, d sub r only depends, or rather, that's not accurate, the way I said it, depends only on r. Okay, this is important. And therefore, now I'm going here to this equation 1. So there, what happens? Equation 1 becomes this on the spherical surface of this bar, which is a constant, ds. Since dr is constant on the spherical surface, depends only on the radius of the surface, I take it out of the integral. And that is equal to q, according to what we found before. Therefore, ds here, that integral equals q. How much is the surface of a sphere? We know that. The surface of a sphere is 4 pi r squared. Do you agree? Do you remember that? You have seen it, I'm sure. Now you need to recover it from your memory. Yes, this is true. All right, so I leave it like that. And therefore, from here, we conclude that this bar equals q over 4 pi r squared. And therefore, since this bar is the only component of D, so then I will have that D, which is D sub bar, A sub bar, equals to Q 4 pi r squared A sub bar. And since D is epsilon E equals D, then I conclude from the above that E, which is the electric field, is therefore Q over 4 pi epsilon naught r squared A sub r. Have you seen this before? How did we find before this relationship? Remember? We found it from where? From Coulomb's law. In this case, I have not drawn the sphere, and therefore, instead of r, I have capital R, I have lower r in my case, and instead of A sub capital R, I have A sub lower r. But we said that when the charge is at the center of the spherical system, little r, lowercase r, is the same with capital R, and therefore this equation 2 is nothing else but what we get from Coulomb's law. Do you agree? This is any questions so far?
Yeah, I have one, Professor.
Yes,
so
go ahead.
that equation that you just derived, by the way you derived it, it's by definition only can only be used by point charges
Yes,
that are independent, have no effects from any other charges in the universe around it, right? Because then
yes,
if it would,
yes,
then
yes.
it wouldn't be
Then you have to
spherically.
superimpose, and that is the next example that I will do next time, is what happens when you have multiple charges. But what I
Okay.
wanted, yes, what I wanted to show you is Coulomb's law is derived from the divergence theorem also. So it's not a postulate. See what I'm saying? It's not like that somebody told us that this is what it is and we take it for granted. Even if it's Coulomb's law, the law came out of the physics of the problem. We use it, we write it, we don't prove it every time, obviously. But I wanted to show you that Coulomb's law is an outcome of the divergence theorem, which is a mathematical construct. You can prove it mathematically without knowing physics. It's interesting, isn't it? So obviously Coulomb, who made experiments at the time, did not, he developed his law starting with experiments, demonstrated, he found out, in fact, something that even mathematics alone would derive. Okay, so that is interesting. You need to remember that. So that's Coulomb's law, and it comes out of divergence. And why am I saying that? Because using the divergence theorem, we are going to find the electric field from all kinds of different sources. If we only had Coulomb's law, yeah, you can derive it from there, but it would have been a little more complex. You will see, I will try to do an example where I will derive a problem using just Coulomb's law. At some point I will do it. I don't want to confuse you right now. And another one through the divergence theorem. And I have to tell you that always the divergence theorem is the winner, because it gives you the simplest way of getting an outcome when you have complex sources. That's all that I want to tell you. The divergence theorem is always a winner. But of course, we want to remember Coulomb's law because we don't want to always derive it. Okay, any questions so far? Was that derivation clear? Okay, so the rest of it here, in fact, is exactly what I said before, but I derived it for you like we were solving a problem. So the next few, here, we're going to do this next time. I will show you how to calculate this in a very easy way. Here it has one formulation, which in fact does not help you very much because it has R1 and R2, all of these different vectors. But so it is a derivation. It is a formulation. It does not give you a final result, but it's a formulation. All right, that's how we call it, something that is formulated. But I will show you next time an example where you, if I know Q1, Q2, and if I know the distances, you can really find the total field in an easy way. Okay? Any questions? All right. So I hope to see you this afternoon. But one thing before you go, because I hear somebody leaving. There is gonna be, I have incorporated, now that I'm here, in your Canvas. If you go, I'm gonna just assign for you one exercise there for this exercise, and this is just based on the force, on Coulomb's law, this exercise. So I will assign it as homework and sign, and I will unassign this one, and I will assign it as a review. Assign. Okay, so this one you guys did pretty good on exercise 3. So now I'm assigning exercise 4 is based on Coulomb's law. And then I would like you to do it until Friday. We have the lecture, okay? Yes,
Professor,
I will post it. Yes.
Sorry. I actually have a question regarding the last exercise 3 we did. So it was just basically the cross product of those two vectors.
Yes.
And C did the cross vector I got was both -8, was 0, -8, -8. So I just chose C because it was the closest to my answer. So I'm not sure if I did something wrong or.
Let me check it. I'll check it and I will let you know. What's your name? I can email you.
Last name's Rustin Deckman.
Might have forgotten the negative J hat or the negative component, because when you take the determinant, that second component.
Yes, the second goes a negative.
Yeah, the second negative. So we have a 0, a positive 8 and negative 8.
Yes. So it's X, Y, and Z. And it's, let me see, 2, 1, 1, and 2, -3. I'll do it right now, -3. And X is, it gives -3 plus 3 gives 0. Y is minus 2 minus 3 and minus that, so 6. And -2 plus with another minus in front plus 2, so it is 8. So you probably forgot the minus of the Y component.
Okay, my apologies. I guess that was
no problem,
Thank
no
you.
problem. Yeah, you're welcome. Okay, thank you. Hopefully we'll see you this afternoon.
Professor?
Yes.
What are you going to talk about during the office hour this afternoon?
I'm going to solve problems that will help you in your homework and other things, because I've noticed we have some weaknesses in remembering some things on using triangles and stuff. And I will help you. I'll give you some hints on how to solve problems easily. So I'll solve some problems, but not your homework. I will solve different problems which will help you solve your homework.
Okay, thank you.
You're welcome. Quiz
Professor,
2. Yes, I will pull. Yes.
Could you show again the Coulomb's law? And
which law?
The force equation.
The force equation. Yes. Wait. This one.
No, the with the 2 charges, yeah.
The 2 charges.
It was the one that you just got to.
This one.
No,
yes.
at the top before, at the very beginning of lecture, I think.
This one? No.
That one right
there. This is the beginning of the lecture.
The one right below there, right there.
Yes.
Could you explain again, like how? So is this force right here the force felt by the small q point charge?
Yes.
Or?
Yes, the small q. So the large q is the source.
Okay.
The large q is the source, the red one. The little q, the green one, is the observer. It's a charge. Otherwise, you have to be a charge to feel force. All right, you have to be.
So, how would you represent the force felt by the source charge? So capital Q from a little q.
Can you hear me from here?
I can now.
Can you hear me?
It's
Yeah,
9
yeah.
o'clock.
Yeah. All right. I'm sorry for some reason. The other thing that I had to, I don't know what happened, but in any case, this I guess is for an hour. I don't know. That sometimes happens. All right. You see that? So Q, the little Q is the observer.
Right.
Yeah. You have to be a charge to feel a force. You cannot feel a force without having charges. So the force is exerted on the little charge when it is in the presence of the big charge. Can you hear me?
Yeah, but
Yeah.
I just can't see the screen anymore.
I know, because it disappeared. You know what happens when it's the Zoom thing? Somehow, and it happens on my iPad, when I go over an hour from the Zoom, it closes automatically while it does not happen on my, I don't know what it is. You might have to do, I mean, I have to extend it to an hour and a half, I think, the lectures instead of an hour.
Oh,
Because
okay.
it closes automatically, and that I had it on my iPad. But yeah, so you have to, the chart, if you remember the picture, the red Q was the source, the little Q was the observer.
Okay. And I think I don't know if you heard my other question, but how would you represent the force on the source charge felt, or the force exerted on the source charge by the observer?
Other one, it's a similar force. And it has, if the charges are positive, it's going to repel both of them. Each one of them feels the same force.
Okay.
Because you can change, you can make the little charge to be the source, the big charge to be the observer.
Oh, so would it be the exact same equation because of the
Yeah,
coordinate
of course.
system there?
Yes, of course.
Okay.
Yes,
Okay. Thank you.
you're welcome.
Professor, I asked, when are we going to be able to see the solution to quiz 2?
Quiz 2. I will submit the solutions today. I will try to do this today, as soon as I can.
Okay, thank you.
You're welcome.